start off by looking at 7.5. Okay? And in the last section, 7.4, we had 3 different groups of identities we looked at. The reciprocal, which is when you flip like sine, you get cosecant. When you flip cosine, you get secant. When you flip the tangent, you get the cotangent. Those ones generally we remember a little bit better because we have to use them on the calculator anytime we want to graph secant, cosecant, or cotangent. Okay? On this kind of calculator, there's no other way to type them in without using the reciprocal. The tangent and cotangent, that was the other group. And the last one was the Pythagorean. All of those groups of identities that we said in our book, they fall under what are called the fundamental identities. Basic, okay, more basic ones. These, they're still pretty important, but they don't fall under that category in our book. Okay, these are called the sum and difference identities. Okay, so first, I want to look at what's on the left and what's on the right. Okay, the problem with what's on the left is anytime you take an argument and you start adding numbers inside, whether it's +3 or -7, or you put a number in front of the x, like a 2, it starts making it complicated to work with. So when we are working with trig, the only thing we generally want inside the argument is a single letter with a number 1 in front of it. Okay? That's all we want. No other numbers. So the question is, if you do have another number inside here, how do we get rid of it? Okay. First thing is I want to look at, can we do what I have on the board right there? Okay. When you have a +3 inside the parentheses, think of it just in terms of a transformation. What does a +3 inside the parentheses do?
Shifted up or shifted down. Or no, it's a shift left.
That's going to be a shift to the left. How much? 3. Shift left 3. How about this one over here? Plus sine 3 on the end. What's that sine 3 going to do? Yeah?
It's going to shift vertically up by sine of 3.
Right. That's going to shift up by the sine of 3. So just from the perspective of transformations, those aren't even the same. So no, what's on the left is definitely not equal to what's on the right. So you can't just do like a distributive property with a function. That doesn't work at all. You can distribute a number, you can distribute letters, but you can't distribute a function. Okay, same thing if I said like the square root of 4 plus 9. You can't like distribute the square root to the 4 and the 9 and say, oh, it's just 2 plus 3 and add them together. The answer to that is definitely not 2 plus 3 at all. It's the square root of 13, which is not 2 plus 3. So you can't apply the function separately to each term under it or in it. Okay? So then what can we do? Well, we're going to look at a few different formulas. Okay? We're going to look at, I don't know how many we'll do today, but there's a situation where we have sine of a sum, that's 1. Sine of a difference, okay, that would be 2. Cosine of a sum, and cosine of a difference. Okay, we're going to look at all 4 of those. We can prove all of them. We're not going to prove all of them, especially this first one. The cosine difference formula, you can prove it. Probably take about 10 or 15 minutes to go through the proof. And for what we're doing, it's just that's a lot of time to spend on that one thing. So we're not going to go through the proof of this one, but we will use this one to prove all the other ones. Okay. So here is what's called the cosine difference identity. So if you have something minus something inside the parentheses, and you want to rewrite it so that the argument is simpler, okay? So you don't have a complicated argument. You can do that. It usually turns into something that has more terms, but you can at least rewrite it so that the argument to each trig function is just a single number or letter. Okay. So the first one rewrites as cosine alpha, cosine beta, plus sine alpha, sine beta. So a couple things to kind of notice in the pattern, because all of them are going to look very much the same. Cosine sum, cosine difference, sine sum, sine difference. With cosine, both cosine formulas I'm going to show you, whatever symbol is here, you put the opposite one there with the cosines. So if you've got a cosine of a difference, when you rewrite it, it turns into a sum. Okay, second thing that happens is the trig functions are grouped together. By grouped, I mean the cosines are grouped together on the left and the two sines are grouped together on the right. So it's always cosine, cosine on the left, sine, sine on the right. And the way that I'm giving you the identities, you're always going to be able to fill in your angles as the first angle, second angle, first angle, second angle. I try to keep that pattern for all the identities I show you. First, second, first, second. So that's called the cosine difference identity. And again, the proof, it is in your book on page 409. Just not something we're going to go through right now. Those are the two pictures you need for the proof. It involves some angles on a circle, specifically a unit circle. Again, we're just not going to go through that. Okay, so what I want to do is, you can do proofs, identities, like we were doing in the last section, but I want to start out just doing something numeric. I want to find the cosine of 15 degrees. And notice I said exact. So that means I don't want any decimals. Okay. So when you're done, you're going to have square roots most likely in your answer. Now from the unit circle, what kind of angles do we know how to work with and get exact answers? What are the kind of angles we used on the unit circle? Yeah?
30, 45, and 60, and 90.
Okay, so how would you
Multiples of
describe?
those. Okay.
What did you say?
Multiples of those.
Yes, any multiples of 30 or 45, we know how to do exact answers with. Right. So the trick to figure out the 15 is to rewrite the number 15 as two numbers. The numbers you pick, though, have to be multiples of 30 and 45. Right. So does anybody see what I could put for an argument using multiples of 30 and 45? And you can do arithmetic like add, subtract. You need to do something with that. I would probably choose subtraction because that's the one we know how to do. And somehow we've got to get 15. Yeah?
45 minus 30.
Yes. So when we did unit circle, I told you there were some gaps that we were kind of missing. Okay. We did the 30, we did the 45, the 30, the 45, and the 60. But there was a gap right there to kind of make them all equally spaced, and there was another gap up there. These two gaps are the 15s, the 15 and the 75. Now that we know the cosine difference formula, we can work with the 15s and the 75s. So it basically adds in 4 more points that we can do in each quadrant. That one would be 105. That one would be 180 minus 15, which is 165. 195. That one is 255. 285. And 345. Okay. But the key is we still need to remember how to do the red ones. If we don't remember the red ones, then we can't do the green ones. So we have to remember everything we've done with unit circle trick. Right? So let's rewrite cosine of 15 using 45 as my alpha and 30 as my beta. So write that whole thing down, but fill in 45 and 30. So it's cosine, cosine, sine, sine. Okay, because I know all of the different identities, I like to break it down. So the first thing I do is I say, okay, what's the pattern of the sines and cosines? Are they grouped or are they mixed? With cosine, they are grouped. Cosine's on the left, sines on the right. Then I say, okay, what's the symbol that goes between them? Okay, I'm dealing with a cosine problem. I always use the opposite of what I have in the argument. That's plus. And now the easy part, fill in your angles. First, second, first, second. First angle, second angle, first angle, second angle. All right. So now, let's start with the cosine of 45. Does anybody remember what the cosine of 45 is? Yep.
Square root of 2 over 2, square root of 2 over 2.
Okay, so the coordinate, yep, if you were going to make your coordinate, it's root 2 over 2, root 2 over 2. And cosine is the
X.
is the x, which is root 2 over 2. Perfect.
No matter which way you chose it there, it's the same as was on the before.
Yes. Okay, now how about the 30? Okay, that's that red, oops, I didn't draw that right. That's the 30. What's the coordinate for the 30-degree angle? Anyone remember that? Yep.
Root 3 over 2 and 1/2.
Good. Root 3 over 2, 1/2. And we want the cosine again,
Which is root 3 over 2.
which is the x, which is root 3 over 2. Good. Thought maybe we were going to get stuck on some of those, but so far so good. All right. How about the sine of 45 degrees? Okay, you already got the coordinates, so now instead of looking at the x value, with sine, you're looking at the
Y value.
y value.
So it's root 2 over 2
So that's root 2 over 2.
times 1/2.
At the sine of 30, the y value is 1/2. So now if we do that out, that's the cosine of 15. Let's multiply the first two fractions together. What's root 2 times root 3? If you put it together.
Is that 2 root 3?
2 root 3 would be if you had like root 3 plus root 3. That would be 2 root 3. Yep.
Would it be 2 square root of 2 times square root of 3?
And yes, when you put that together now as one square root.
It would just be, oh wait, as 1?
Mhm.
I think that would just be square root of 2 plus 3. No, inside the root.
No, it wouldn't be a 2 plus 3 when we combine it.
Oh, it'd be 6.
6, yeah.
Which is basically
Okay, so square root of 6, and my denominator on that would be, yep,
4.
4. You're multiplying. All right, and then your second fraction, what's that one going to be? Yep.
Would be square root of 2 divided by 4.
Square root of 2 over 4. And now I want to put those two fractions together, so what do you need to have in order to add two fractions together?
Denominator, which it has.
Yeah, we're going to always have it. It's just the way these are going to work out every time. So we can put it together as one big fraction the way it is. And that should be the exact answer for the cosine of 15. How can we check that and see if it's right? Any ideas what we could do to verify? Yeah.
Put it in the calculator.
Yeah. again, the calculator's not going to give us an exact answer, but it will give us a decimal. And if the decimal I get from my answer and the cosine of 15 come out the same, then chances are we did it right. Okay. Make sure you put your calculator in degrees, because that's how we did this one. If you ever get one in radians and you're not comfortable doing all that arithmetic in radians, then you can change the radians to degrees to start the problem. So you could do that step first. All right, so that's the cosine of 15 degrees. Now let's do root 6 plus root 2 divided by 4. If you're going to check it, that's how you have to type it in with those parentheses. And the answer that we got is exactly what you should get. Any question on that? So when you are dealing with sine and cosine with any of the 15s, any multiple of 15 or 75, well, it's a multiple of 70. It's a multiple of 15. No, the other way around. If it's a multiple of 75, it's automatically a multiple of 15. You're always going to get some root 6s, some root 2s, and a divided by 4. Okay? You'll always get something like that. Could be root 6 minus root 2 over 4. Could be minus root 6 minus root 2 over 4, but it's some combination of a positive and a negative root 6 and a root 2, and a divided by 4. When you're dealing with sines and cosines of 15s. All right. So any question on that one? Okay, so that's the cosine of 15. Okay, let's try this one. So this is more like what we did in the last section, but it's a lot easier because this formula is pretty much going to guide you through all the steps. In the problems we did in 7.4, sometimes you kind of have to be creative and figure out, like, okay, what should I do to change this into that? There's nothing creative to think about here. First, identify which side looks more complex, the left or the right. Yep. Yeah, the left has 2 terms for the argument, the right does not. So left side is definitely more complicated. And the left side fits a pattern for a formula that we just learned. What's the pattern that this formula fits? It's called the what? Yep.
Cosine difference formula?
Yep, that's a cosine difference. So we're going to rewrite that using the cosine difference. This is going to be your first angle. That is going to be your second. Okay, so let's try to start thinking about writing it down, because once we know all the identities, it gets a little harder to remember which one's which. Okay. It's a cosine difference. When you do a cosine and you rewrite it, do we group the trig functions or do we mix them? Yeah? Group. Yeah, you'll know what I mean by mixed. You'll have one of each, but we group them. Cosine, cosine. Sine, sine. Okay, so that's the first part. And then we have a minus in the argument. What symbol is going to go in the rewrite? Yeah? Right. With cosines, you do the opposite. With sine, you don't. You do the same. So it's a lot to keep track of. Now fill in your angles. First, second, first, second. Pi over 2, theta. Pi over 2, theta. Anything with a theta, you're not going to be able to simplify, but a pi over 2, yes, that will simplify. So somehow this entire left-hand side is going to reduce down to sine. Let's see how. Let's think about our unit circle. Pi over 2. Where's pi over 2 on the circle? Yep.
I would choose on the coordinate 0, 1.
Right, it's the coordinate 0, 1
For 90 degrees.
for 90 degrees. So now we've got our x and y. Let's apply it and see what we get. What's the cosine of pi over 2? Yep. 0. It's the x value. So 0 times cosine. That's always nice when that happens. Plus What's the sine of pi over 2? Yep, 1. It's the y value of the coordinate. And what's going to happen when we do 0 times cosine theta? Right?
Just gonna equal 0.
Right, that's gone. That cancels out, so we don't need that anymore. And what's 1 times sine theta? Yep,
Just sine theta.
just sine theta. So that is how the left-hand side turns into the right. And that's it. So what, if you want to think of this in terms of a transformation, what you're basically saying is, if you take the cosine function and you shift it to the left 90 degrees, and then do a horizontal reflection to it, it will look exactly like the original sine function. That's basically what you're doing. A 90-degree left shift followed by a horizontal reflection of cosine results in sine. That's it. All right, let's try this one. Okay, so what are you proving in this one? Well, I like to think of it with the letter first. You don't have to think of it that way to do the problem, but if I want to think of it in terms of like a graph, I would think of it like this. And what I'm trying to prove is that if you shift the cosine function 180 degrees to the left and reflect it horizontally, it's the same as doing a vertical reflection of cosine. It'd be the same thing. Okay, so start with the side that's more complex. It's going to be our left-hand side. Now, can anybody rewrite that entire left-hand side for me, like we did in the last problem? Without me kind of stepping you through it one step at a time. Yep.
Would it be cosine pi times cosine theta
Yep.
plus sine pi times sine theta?
Perfect. So now we have to work with the two that we can simplify, where the arguments are pi. Okay. Where's pi on my circle? Yep.
-1, 0.
-1, 0. Okay, so there's your coordinate. That tells you everything you need to know to do the sines and cosines. What's the cosine of pi? Yeah, -1. Okay, so you have, oops, got extra parenthesis. So we have -1 times cosine. And what's the sine of pi? Zero. 0 times sine theta. -1 times cosine is negative cosine. And then 0 times sine, well, multiplying by 0 is going to get rid of that. So the left-hand side turns into negative cosine. And that's exactly what they wanted me to get. So this, again, still, when somebody asks, do we still need to know how to prove the trig identities? Yeah, okay, but these ones are much easier. Some of the other ones we do later on, they are going to involve the formulas from section 7.4. Probably not today. Okay, so that's the cosine difference formula. Okay, there's two things to figure out the cosine sum formula. There are two things we have to remember. What that equals and what that equals. when you have a negative inside the argument, we looked at this, it's probably back in chapter 6, so it's been a little while. You can get rid of these negatives inside here, but in different ways. Does anybody remember when you have a negative inside the cosine function, what you can do to get rid of it being inside the function? Yeah?
Isn't cosine like horizontally symmetric, so you can just get rid of the negative sign?
Exactly, perfect. Cosine
No.
is symmetric.
Vertically symmetric.
Yeah, it's symmetric over the y-axis. So because there's a line of symmetry on the y-axis, reflecting it horizontally does nothing to the cosine graph. So when you have a negative inside cosine, you can just get rid of it. Try it on the calculator. Try the cosine of negative 10, try the cosine of positive 10. You're going to get the same answer. Now, with sine, you can't do that. The sine function, if you draw the sine function, it looks like that. If you reflect it horizontally over the y-axis, like this point would end up down here. So no, it doesn't land on the same thing if you flip it left to right. But it ends up down there. So does anybody know what we can do with the negative in that case?
You can put it on the outside.
Yep.
Because it's vertically symmetric.
So we can put it on the outside in the front. Okay, so we're going to derive the next formula, but we need to remember these two things. Okay. So we just went over that. Now, let's see if we can figure out the cosine sum formula. Well, right now we know the cosine difference formula. So somehow we've got to work with that. Can somebody tell me how I could rewrite this problem as a difference? I need something here, and I need something there. And what's in those two boxes are going to be my first angle and my second angle. But I need to rewrite that. Yep.
Wouldn't that be alpha minus negative beta?
Perfect. Yep, alpha minus negative beta. So now if you're like, well, what's the point? We've rewritten this as a difference. And now we can take that and fill them into the formula we already know. And whatever we get for the answer, that's how you do the cosine of a sum. Okay. So let's break that down. Okay, let's go through it. Trig functions, are they grouped or mixed for the cosine difference? Yeah, grouped together. Cosine, cosine. Sine, sine. What's going to go between them? Plus or minus? Nick, what goes between them?
Plus.
Yep, I'm going to put a plus. Now fill in your two angles. Alpha is in that box. Negative beta is in that box. Right there. Okay. Now, we can't leave the identity with that negative. We always want to write it so there's a single thing inside the argument, just a number, and a 1 in front of the the Greek letter. Okay. So how can I fix cosine negative beta so there's no negative inside? Yep.
Do you remove the negative symbol?
And put it where?
You don't need to put it anywhere because it's symmetric.
Yeah, just get rid of it. You don't need the negative. Okay, just completely get rid of it. And now on the last one, sine alpha. How can we rewrite sine negative beta? Yeah.
Negative sine.
Right, we can put the negative, I'm going to put it in front of the whole thing, which is really going to turn this plus to a minus. So there's my minus in front. And there you go. So that's your formula for the cosine of a sum. So that also proves to you anything you can do as a sum, you really could just do it as a difference. You don't actually need the cosine sum formula if you think of it this way. Right? But it is easier to remember it, so you don't have to think of doing a problem as minus a minus. All right. So now, let's try this one. Cosine 75. Now, if you didn't know the sum formula, you could think of that as a difference. Okay. But I would like to try it as a sum. Anybody think they could tell me how I could break that up as a sum, but you have to use angles that are multiples of 30 and 45? Like if you did 73 plus 2, well, I mean, that's 75, but how are you going to work with a 73? We only know how to work with 30s and 45s. Yep.
That would be 45 plus.
Yep. And if you're stuck, you're like, well, how would you do that as a difference? Well, there's different ways you could do it, but you could do 130. No, actually, you tell me. What could you do if you wanted to write 75 as a difference? I almost started to say it, but. Let's see how you could write 75 as a difference of two numbers. Yep.
Could you do 135 minus 60?
Yep, exactly. You could do 135 minus 60, and you would get the same result. Yep. Right, but I'm gonna do it as a sum. So cosine, cosine, sine, sine, and now what's going to go between them? Yeah, a minus, and then we fill in 45, 30, 45, 30, and we've already done all of those problems earlier today. Cosine of 45 is root 2 over 2. Cosine of 30, does anybody remember that one? Yeah?
Root 3 over 2.
3 over 2. Sine of 45, root 2 over 2. And the sine of 30?
1/2.
1/2. So the answer looks very similar to what we had when we did 15. It's root 6 minus root 2 all over 4. So that's the cosine sum formula. Okay. Any question on that one? And you can do the same kind of thing that we did, where was it? Right here? You can do it with a sum and do verifications, just like that. All right, so now you've got the cosine sum and the cosine difference. Let me give you, you know what, I'm going to do it this way. All right, well, we can try this. So we know there's a connection between sine and cosine. If you remember, they are horizontal shifts of each other. Because of that connection, because sine and cosine are very similar, we can figure out the formula for the sines because we already know the formula for the cosines. We could prove this, okay? And we've done one very similar. In fact, did we prove that one? Not quite. We proved something a little bit different. negative theta plus pi over 2. This is, well, negative theta plus pi over 2. Yeah, that's the same thing. So we did prove that. Okay. That was an earlier example. We proved that what's on the left equals what's on the right. So now, let's see if we can rewrite a sine problem as a cosine problem. Okay. Just like when we didn't know how to do a sum, we rewrote it as a difference because we already knew how to do that. We're going to try to rewrite this as a cosine problem because we already know how to do that. Let's see. All right, so anybody see how we can rewrite what's on the left there? I'm going to give you a hint. Okay. We don't have sine of alpha or sine of theta. We have sine of this. So I want to apply this identity, but instead of plugging that in, I want to plug that in right there. And that's going to turn this from a sine. I just need to tell you to tell me what would be on the right side if we do that. Yep.
Pi over 2 minus alpha minus beta.
Right. It's when you change a sine to a cosine, it's pi over 2 minus whatever you had right there. In our case, I'm trying to prove the sine sum formula. That's why I put a sum. If I was doing the difference formula, I would have put a difference. Okay. So it's pi over 2 minus whatever's in the box right there. That's how you turn a sine into a cosine, and we proved that. All right. Now, I'm going to regroup this right-hand side to look a little bit more friendly and help us do what we need to do. I'm going to regroup it as pi over 2 minus alpha. So I'm basically distributing out that negative. I'm going to have that, and then I'm going to put minus beta. So I'm just distributing out that negative. What I have now is a cosine difference formula. This is my first angle. That is my second angle. So now apply the cosine difference formula using what's in the red brackets as 1 and what's at the end as 2. And that will give you the sine sum formula. So every formula we're figuring it out, we're going back to a formula we already know, trying to rewrite it that way. And then that'll give us a shortcut in the future. So now we'll have the formula, won't have to do that again. All right. So cosine, cosine, sine, sine. Okay. This is cosine of a difference. So what symbol is going to go down there? Yep.
My symbol. No, wait, plus.
Plus. It's always the opposite. And then for my first angle, I'm filling in pi over 2 minus alpha. For my second angle, beta. Pi over 2 minus alpha and beta. Not going to be able to do anything with the betas. Those we can't do much with. But look at the identity we have up here. We don't have the exact same thing down here. Well, this one we do. What is that the same as if we look up above? Yeah?
Sine of alpha.
Sine of alpha. Now, This one we did not prove, but it's very similar to the one we did prove. Does anybody have a guess if we went through and proved that one, what the sine of pi over 2 minus alpha would be the same as? It's very, very similar to this one. Yeah?
Negative cosine of alpha.
Nope, even simpler than that. So if you take cosine of pi over 2 minus theta, you get sine. How about the sine of pi over 2 minus an angle? What do you think you get?
So that would be just cosine of alpha.
Yeah, it would just be cosine. Okay, we did not prove that one, but we could. So notice the pattern you get when you do the sine of a sum. The trig functions are mixed. It's a sine, cosine, cosine, sine, and whatever symbol you had here is the same is what you put there. Okay, so that's the sine sum. And then the sine difference, it's pretty much like the sine sum. They're mixed, sine, cosine, cosine, sine. And whatever symbol you had here is the same symbol you put there. Okay, so those are the sine, sum, and difference identities. And that's what we'll stop with for today. So now you could do things like sine 15, sine 75. You could do it the same way. Just break it up into 30s and 45s and follow this pattern. But you're going to get the same root 6s, root 2s, and the 4s in the denominator. Same thing.
So are we solving it for anything yet, or are we just getting that?
What you can do with these right here is exactly the same thing you can do with examples 1, 2, and 3.
Okay.
So you can do the same stuff we just did with cosine, except now you can do it with sine. Okay, so for the homework, I'm going to change that. So, 1, 3, 5, 6. 11. That's it. 1, 3, 5, 6, 9, 11. All right. And we will take a look at that tomorrow.